my name is Jason Biggs. I have been working for Wolfram Research for the past 5 years, originally with Wolfram Alpha, and then more recently developing kernel functionality. My background, I first became introduced to Mathematica when I was a PhD student, and what I really enjoyed about it was the ability that when I was a theoretical not a theoretical student, the student of theoretical chemistry, and so we would derive equations to describe the spectroscopic signals that we imagined generating with our theoretical experiment, and then I, who had no programming experience before coming to grad school, was able to just translate these equations almost directly from the paper into the notebook and really get started almost right away in generating these simulated signals that we would use to publish in papers. And over my time in grad school, I got better at programming. I learned to be more efficient, but what I really liked about the Wolfram language is that the ability with a notebook to just to prototype things, to explore in the notebook interface, and then eventually you get the code down that you like, and then you can transfer that to some source file, or keep it in a notebook and run your program from there. But yeah, since joining the company, I've learned other programming languages as I have worked to expand the capabilities of the Wolfram language in chemistry. But I still am just, in general, really excited about working in a notebook. I think, I still find that ability to prototype a function, get everything working the way you want it, and then transfer it out of that development environment into a more production style environment. And yeah, so that's my background. And then now I'm going to turn off my camera here and begin the presentation. Okay. Let's see, this guy should be bigger, right? All right. Chemistry notebooks for research. Let's see, let's go through a little bit of the history here. So Mathematica is now on version 12.3, version 13 coming shortly. I think it was first in version 6 that these new data functions started to come out. And so with it, most importantly for me, was chemical data, which gives you access to thousands of chemical entities with data that's been curated by people who work here. So you can access their melting points, the boiling points, their identifiers in various databases, and and so that's what chemical data allows you to do. But more recently, we've come up with the molecule function that allows you to create any type of molecule that doesn't have to exist in any database, and so it becomes literally uncountable. All right, so the basic capabilities for using the molecule is that you can create a molecule from any kind of identifier. You can generate 2D structure diagrams or three-dimensional conformations very quickly. You can search for and highlight chemical substructures. Then you can modify those molecules by adding and deleting bonds or doing a force field geometry optimization. You can also import data from other sources and export data to be read in by other programs. I think those are very important points also, that the next time I give this talk, they should be their own bullet there. All right. So I like this timeline plot here. Basically, you see that things have kind of ramped up for chemistry. So Mathematica 1.0 came out in 1989. Chemical data came out in 2007, and then since then we've just been adding to the knowledge base. So I talked a little bit about chemical data, how the basic syntax that you've got a chemical entity and then a property. I do believe that this was touched on in one of the previous talks, so I'm not going to go too into detail about this. But also very important here is thermodynamic data, where we have access to let's see, various types of thermodynamic properties for a subset of chemical entities. These are chemicals that are of. So this draws on data that is released by the National Institute for Science and Technology. So we have a very good source for thermodynamic data. And if you need to know which entities does thermodynamic data work with, then you just do thermodynamic data, open, close, and you see the subset of chemicals that for which extensive thermodynamic parameters are available. All right. So that was in version 6. Then shortly thereafter, in version 10 came entities, right? And so the range of real-world objects which are represented as entities in the Wolfram language greatly exploded. So previously it was chemicals, elements, maybe countries, but now if you want to know the different types of entities that are available in the Wolfram language, you let's see. Yeah, so this is the full list of entity types that are available in the Wolfram language. And so this is the main connection between Mathematica, or the Wolfram language, and Wolfram Alpha. So this is what the people who work with Wolfram Alpha work on, is finding out all these entities and getting the curated information and making them available to you through entity value. And so entity value has a similar syntax to chemical data, except for you've got an entity. Let's see, let's look at trichlorofluoromethane here, and then we want its adjacency matrix. And there we go. And so this is so you've got an entity and a property, and that's the basic syntax. You can ask for all the different types of properties that are available for chemicals, and you get this list. Now, obviously, all of the, or maybe it's not obvious, it should be stated, not all of these properties are populated for every entity. Especially melting points and boiling points aren't available for every type of entity, and various other properties are more sparsely populated. But this is continually being added to and continually being updated. Right. So I'll leave these examples here in the notebook that you can go through if you like. Another big, very important point is service connections. So the one that I find incredibly useful is the connection to PubChem. So PubChem is a public database that anybody can contribute to. So any chemistry lab that creates some new substance, they can submit a substance record to PubChem. And if the substance that they've submitted corresponds to a new chemical that is not in their database, a compound record gets added. And so in PubChem, there are nearly 100 million compounds. So a substance record would be any instance of a compound. And they're not unique, whereas the compounds are unique. So there are nearly 100 million unique chemical compounds in PubChem. And a lot of them do not have a great deal of experimental data for. A lot of them only have the type of data that you can compute from a given chemical structure. But regardless, you connect to it via the service connect, and then PubChem. Let's see, if you want information about if you want information about PubChem, just search the word PubChem on the documentation database, and it will pull up. The way I have my screen share set up right now. So all you basically have to do is double-click PubChem and hit F1. The documentation page will pull up for it. But it didn't show up on the screen here because I'm sharing just one window instead of my desktop. But it's a good documentation page, describes the syntax. you create a service connection to PubChem, and then you query it for the various types of queries that are supported. So in this case, we want to know the compound description of the compound whose international chemical identifier is given by this particular string. And it turns out to be chlorine dioxide. And you get all this information back just from the call to PubChem. Right. So then now in version 12, we came up with the molecule object, which essentially is a graph, right? If you're familiar with Wolfram Language, you know that you could make a graph here, and we give it a list of vertices, 1, 2, and 3, and it's got edges. There's an edge from 1 to 2, and an edge from 2 to 3. And that's the basics of that's the basic network structure, right? But then for a molecule, you need to identify that these vertices, this vertex corresponds to an oxygen atom, these two vertices correspond to hydrogen atoms, and the two edges between them correspond to single bonds. And so that's basically what molecule is. It is a decorated graph. It is a vertex and edge annotated graph. That's the description of the data structure. But basically, what you need to know is you can create a molecule through various different constructors. You can give it a string with a name or a smiles. I'll go through that in a little bit. But then it evaluates to this form, where it has the list of atoms, the list of bonds, and then a list of options. So in that list of options can come things like atom coordinates, stereochemistry elements, and other bits of meta information that you can just put in there. So you can query for the atom list and the bond list using the functions atom list and bond list. And you can get the various properties by first assigning. So here what we do, we say mole equals molecule of water. And then so we know now that after that, let me go ahead and evaluate that. And then after that, mole is now no longer in blue, so it's an assigned symbol, and it's actually assigned to water. So now when we say use it as the head of a function, we are it's called a subvalue in technical speak in Wolfram Language. So we're asking for the subvalue of this object. And so in this case, we want to know its molecular mass or its point group, right? And so water has a molecular mass here of 18 unified atomic mass units, and then a point group of C2V. So notice that said point group display, and that's because if you wanted something more computable, you would ask for the point group string, and that's just C2V. And so that would make it easier if you were writing a program that said, PG equals point group of mole, or mole point group, and then if PG equals C2V, do this, do that. It's much easier to compute with strings than it is with something that has a subscript. So again, so another interface you can ask, you can use this subvalue where you give it a string operator, but you can also use this function here, molecule value, which allows you to pass in multiple molecules and multiple properties and to get it in a faster, more efficient manner. So you can get the adjacency matrix just like we did earlier with from chemical data, and you can do a matrix plot. You can do any types of matrix operations that are available in the language. You could also change the molecule. You can set the mass number for the two hydrogens equal to 2, and so that essentially gives you now deuterium oxide. So I mentioned smiles string, and basically what a smiles string is it's a string encoding of molecular structure. So what you can do, the basic unit of a smile string is an atomic symbol wrapped in square brackets. So here we have xenon. So this is a molecule, and so it's not technically a molecule in the scientific terms, right? Because it just represents a single disconnected atom, and you need, I think, via the IUPAC definition of a molecule, has to have more than one atom. But what we're dealing with here is a symbolic representation of a molecule. It's a data structure, right? And so the data structure allows you to have disconnected atoms. It allows you to have just one atom. It would allow you to have no atoms, right? Wait. Oh, wait. So we have to give it an empty list of atoms, empty list of bonds. And so then, and so that's a convenience for programming. You want the data structure to behave the same for different for an atom count between 0 on up to however much memory you have, right? And so a molecule here with xenon wrapped in square brackets corresponds to a single lone xenon atom. Two atomic symbols together with nothing between them represents a single bond. Let's see if I did that. There we go. We get molecular hydrogen. Whereas if you put an equal sign, it becomes a double bond. Or you put the pound sign, and you get a triple bond. And notice here, you will get an error when stepping outside of the normal accepted valence states for atoms. But after you get that error, you still have an object that should work in all the various situations you need it. So in a smile string, you can also indicate charge inside that, or you can indicate an isotope. For the common organic elements, carbon, nitrogen, oxygen, sulfur, chlorine, you do not need the square brackets. So when you just put a C, it interprets it as being carbon with as many hydrogens are needed to fill up its valences. So just C corresponds to methane, CC to ethane. Whereas if you bring back those square brackets and don't tell us how many hydrogens are in it, this is how you get a single molecule with 2 carbon atoms and no hydrogen atoms. And so if you look at its atom list, you'll see that the only way that makes sense is to give each of those carbon atoms an unpaired electron count of 3. Right. So then there are lots of interesting things that you can do with smile strings. Right. An important thing to note is that you can close up a ring by marking one atom as, so this says here that this first carbon is labeled atom 1, and then here at the end we have a callback to that. And so what that means is that this last carbon is bonded to whichever atom was 1. And so that's how these two strings, these two smile strings, correspond to let's see, this tricyclo, or this is hexa 1, 3, 4 triene, something like that, right? And then this is benzene. And actually, we don't need to figure that out. There's a function that came out in version 12.2, and we can look up. So it's, 3E hexa 135 triene. I was close. I just forgot the stereochemistry, right? Okay. So we can also understand chemical names. We have access to a parser that runs locally. This is the Opsin parser. It runs locally on your machine, and so it can turn these chemical names into a smile string without needing to call any database, which can make it actually very quick. And so we can create 4 different molecules off of 4 different strings. 1, 3, 2, 4, 4, 6, or meta dichlorobenzene, and we can find that they all eventually create the same molecule. the actual function that will convert any chemical name into a smile string is available as a resource function. I believe you should be familiar with the Wolfram function repository. It's a place where functions that are not in the system context can go, and it's a place where people who are just Wolfram language users can submit functions. People who work here sometimes submit functions. Many a time I've come up with a function and then we in the team meeting say, that looks neat, but I don't think that needs to be a system function, and so it ends up being a resource function. In this case, it's called name to smiles, and so it operates on 4-chloro-6-chlorobenzene and returns this smile string. So when you create all of these molecules, they all come out to be equivalent to each other, but they could have their atoms in different orders. They could have their bonds in different order. And by order there, I specifically mean the order of the list, not the bond orders, right? Okay. So what we can then do is, after we create these 4 molecules from 4 different strings, is we could ask, are they equivalent to each other? And it will come back and say that yes, they are. So that, yeah. So that's that. We already touched a little bit on molecule name. So essentially, it's the way to go backwards. But it does that is not done locally, right? So creating a molecule from a name is done locally. We parse that and convert that into a smile string. But generally speaking, if you need to find the name for it, we need to look it up. And so we have the function called molecule name, which will query first the Wolfram knowledge base, or Wikidata, or PubChem to find the name of the molecule. And so that's actually where those smile strings come in really nice, is because when you can take your structure and you convert it to a canonical smile string, you can then send that smile string to the database and ask them, do you have any records with that match this smile string? And in this case, they do, and it comes back psilocybin. And so that is the name that was stored in the Wolfram knowledge base. But if there's a 2-argument form of molecule name where you specify the source, and PubChem thinks that this molecule is called 3,2-dimethylaminoethyl 1H indole 4-eel dihydrogen phosphate. And so I always think that those are neat, going back and forth between the chemical names and the structure. Okay. Another thing that I find to be really important is in being able to interchange these molecule structures with other programs. And so there are several file formats that have come out specifically for this to allow interoperability. So there's the SD file, structured data file, right? So I have this particular SD file that I downloaded, and I think it was somebody had taken a bunch of patent files and used text mining to grab molecules out of it. And so if I just ask import to take that file and give me the molecule count for it, it will go through and starting at the beginning, scan through and count how many records there are. And it can tell you that there are 275,000 molecules in that. And so importing those would actually take some time. And let's say instead of importing all the molecules, I want to go to import a span. So what this span here says is from molecule 1 to 200,000 in steps of 5,000. So essentially that's going to import only 40 of the molecules. When you import a molecule from an SD file, it can come with both meta information and structure information. And so that's what makes the SDF file useful. XYZ is another common file format. So if you get data from an electronic structure calculation from Gaussian or MolePro or something, then you're going to only have the atomic positions and the names of the atoms. You're not going to know what the bonds are, because the bonds are a result of the electronic structure calculation, not really an input. The electronic structure calculation only cares about the electron density. The bonds a way for us to think about those. So when you've done an electronic structure calculation, you might only have an XYZ to represent the geometry. And so when you bring it in to the Wolfram language, it'll oftentimes have information missing. So here, let's do this. Let's say M equals this molecule. We generate 3D coordinates for it and we plot it. Here we have it. And let's go ahead and export string of that in a SD format. So this just gives you the atoms and their atomic coordinates. And then if we import it, then it has to figure out the bonds on the fly from that guy. And so that's actually pretty interesting. Let's skip over CIF and CML, and then let's see. So one last thing here. Let's say you were doing that electronic structure and you did a Gaussian, right? So then you might have a formatted checkpoint file. You import the molecule from that formatted checkpoint file, and it's got 3D structure in it, and it also has meta information. So this would be all of the information that was scraped from the SD file, and it's stored in the molecule object itself under the meta information option. So you'll have things like the dipole moment, the orbital energy, the orbital occupations, and that kind of thing. It would be nice, a planned improvement in the future would be able to take a formatted checkpoint file and be able to plot the orbitals themselves. Currently, we cannot do that, but what you can do is if you've done some kind of calculation in Gaussian or some other package, then you can get volumetric data. You can get a cube file. And so what that is essentially you take a volume of space that's big enough to hold the molecule plus all of its electrons, or 99% of the electron density, so to speak. And then you break that up into a three-dimensional grid, and you evaluate the density and write it down to the file at every point in that density. And so you end up with a file that looks like this, where initially you have the 3D structure, the 3D geometry, and then followed by a large table filled with the values of the electron density at those points. So when you take that file and you import it, what it returns back is a molecule. The molecule has all of that structured data stored inside it. So you'll end up seeing something like this. It says data not stored in notebook. And so that's an interesting point. When you do a calculation in a Wolfram notebook, the result is printed out in an output cell, and sometimes the output from that is very large, so large that if you hit save in your notebook could become hundreds of megabytes, and that is not always the desired outcome. And so oftentimes, just because you have a variable in memory that has a lot of data to it does not mean that you want it serialized. And here serialized means written out in a form that could be read in later in your notebook. And so in order to avoid making notebooks huge and making reading the notebook slow, you get this button that says the data was not stored in the notebook. It's still in memory, and if you want it to be stored permanently in the notebook, you press the button here. Okay, so the reason that it's so large is because it's got this numeric array that's 78 by 78 by 80 set of real numbers. And so what you can do with that is plot it using a contour plot 3D. And so here you can do that directly by using import of the cube file and tell it you want the graphics 3D. You can pass options to it and telling it with the contour style and the plot legends. And so essentially what this is, these are isosurfaces of the, let's see, so we've got, this is not the density, then this must be the wave function of this particular orbital. And Yeah, and so you could set the value of those contours that you want to plot, like this. You can give it a contour style saying that you want some opacity. Right, so this is an example of a wave function, and here we have an example of density being imported because you see it's all positive. So another thing that another really powerful thing that you can do in Wolfram language with molecules is by searching for and highlighting arbitrarily defined substructures. And so, right, so let's just jump in here. We can define patterns for various types of atoms. So this would be a pattern. This would match anything that is any type of oxygen atom. Here we can write a pattern for any atom with a positive formal charge. So it's an atom with a formal charge is greater than 0. Or we can say any atom in a ring. And the way we write that is atom ring member Q goes to true. The different types of properties that you can specify in these are available on the atom documentation page. So we define these various patterns for types of atoms. We can define labels for them and then come up with these highlight rules. Essentially, we say oxygen atom goes to O, so the label and the pattern. And so if we wanted to, we could take a molecule like, so in this case, we've got molecule trinitrotoluene. I'm going to hit Command Enter here and evaluate it in place so that you can see what it looks like. And so what we do is we find molecule substructure of the molecule and then the substructure pattern. So in this case, we just want to know where are the atoms with a positive charge, and we want all matches. And so we find that they exist at positions 4, 9, and 14. We can plot them. So we can take those highlight rules up here and we can plot them, and you can see the oxygen atoms, the cations, and the ring atoms. And remember, we defined these labels up here in this association. Let's see. We can also define patterns for bonds. So this would represent any nitrogen-nitrogen bond or any bond between a halogen and anything else. So if you look at this, it's got the head bond, so it's going to match a bond. The first atom uses alternatives, which you should know that this little pipe here matches alternatives. I assume people have a good understanding of mathematics or of a Wolfram language here, but let's just remind ourselves what the alternatives means. So we can do match Q 3 2. No, 3 does not match 2. But does 3 match 2 or 3? Yes. So it's within a pattern, you can think of this single pipe character as being an OR. But it is not OR because OR is the double pipe. So you have to keep those two things in mind. The logical OR is different than, and that's why we have the word alternatives. So, okay, so what this means is the first atom of this bond can be a chlorine, fluorine, bromine, or iodine, and the second atom can be any kind. And so you see here in this molecule plot, it matches the carbon-fluorine bond. You can make more advanced patterns here. So this is a bond between an atom with a positive partial charge and an atom with a negative partial charge. And this is labeled as polar bonds, and so it matches this carbonyl in this particular molecule. And you can use the actual head molecule pattern, which give it a structure similar to what you find in molecule, where you have a list of atoms and a list of bonds, and then this represents any carbonic ester. And let's see, so this will visualize now. So we can do, right, so this is a pattern for this type of substructure. And then you can highlight it here in this molecule in 3D or in 2D. And if you want to make changes to the molecule, there's one big function called molecule modify that has a lot of different types of modifications. If you want to add an atom, you let's see. So you do molecule modify the molecule. In this case, we're doing add bond, but you can do add atom, add bond. You can set the formal charge. Let's see. So all of these are listed not only in the documentation page, but they're also available through auto completion. So we say molecule modify mol, and then start quotation marks, and it opens up all of the different types of modifications that are available. You can take a molecule that has 3D coordinates and perceive its stereochemistry from it. You can take the atom coordinates that you brought in and canonicalize them, which means moving the center of mass to the origin and moving the principal axes to correspond to the Cartesian axes. You can delete atoms or bonds. You can turn aromatic atoms into single and double atoms. You can renumber the atoms. It's kind of one, let's just call it the kitchen sink of a function, right? It does a little bit of everything. Or no, let's call it the jack of all trades. Generally speaking, it will try and fix valence errors when you work with it. So if you took phenol and you converted, you wanted to set the formal charge on an oxygen atom to -1, well then by default it's going to get rid of that hydrogen atom to avoid a valence error. Because if you have an OH and you want to, if you have an oxygen with 2 bonds and you want to set it to a formal charge of -1, then you should get rid of one of those bonds. And so hydrogens are discardable at that point. But if you don't want that to happen, you can pass in the option to avoid valence fixing. Right. So, and there's more here about modifying molecules. And then I have a few applications here. Like this one I think is actually pretty neat. So I moved it up in the slides from where it might normally go. So let's see. So this is molecular shape analysis. You want to know, general, out of this collection of molecules, you want flat molecules, or you want molecules that are long and skinny, or molecules that are rounder. And so what we do here is we're going to create a principal moment of inertia and plot. So let's see. Well, first off, we'll pick 3 kind of extreme examples for shape: the linear, the rod, the disk, and the sphere. And we'll evaluate that. We'll have these 3D plots. But I've set them in a graphic row, so that's why I can't move it at the moment. But okay, so if we were to look at the principal moments for these guys, then for the rod, you see that the first is basically 0, followed by 2 identical principal moments, and then the disk will have 2 small and then a third one larger, and then the sphere has basically 3 identical. So obviously a true sphere would have 3 identical principal moments, but this is only an approximation thereof. Right. So what we do now is we take the principal moments and we divide the 2 smaller moments by the largest, and we end up with the normalized principal moment ratios. Or if you see these in literature, it could be the NPR. So if you look at those for the rod, disk, and sphere, you see it's basically 0, 1, half, half, or 1, 1. So if we use those in a 3D plot, then let's see. First, so if we use the normalized principal moment, the NPRs, as coordinates, then the 3 extreme cases that we came up with before form the corners of a triangle here. And so we can take a set of molecules that I've prepared ahead of time. It has, let's see, 303 molecules in it. And so what I'm going to do here is I'm going to do a list plot of them. So let's take a real close look at this. So what I'm using here is a resource function called dynamic map. And so it's mapping a function over a list. And map is a normal system function, but dynamic map essentially does mapping but gives you progress reporting. It's very useful. So then what I'm doing here is I'm wrapping the coordinates. So I'm mapping over the list of molecules I just created here. And the thing I really need most is the normalized principal moment ratio. So you remember that's going to give me a list of two numbers. So that's my XY coordinates. And that would be enough to give the list plot. But I'm going to instead wrap it in a button, which says that basically anytime you click on one of those coordinates, it'll do the second argument to button. So here, button, the first argument is the coordinates, and the second argument is the button action. And so what it does is it copies to the clipboard whatever the argument there was, and the argument is going to be the molecule. And then I wrap that in a tooltip with the second argument being a 3D plot. And so I believe last time I ran this, it was actually fairly speedy. So let's make sure that it is now. Computer's running a little bit slower with the meeting going on, right? But it's still a little bit peppy. So it's generating 3D coordinates for all of these molecules, and then it's computing their normalized principal moment ratios and computing a 3D plot for them, all in the time that we're waiting here. And if I wasn't running the screen share, it would happen a little bit faster. But we're almost there, and I don't have to keep talking anymore. All right. Wait. Right. So now we end up with this plot. And so, like I was saying before, you have tooltips. So I'm using a screen grab to show what that tooltip would look like. So yeah, so that's what it looked like when I hovered over one of those points. But as I hovered, the molecules up here were very up in the upper left corner were more and more narrow, and then you missed the buckyballs, the more football shaped. But this example should evaluate in your notebook. And so this is one of the things that I really love about the Wolfram language, is that I can just, with a simple call of list plot, and this here is this list, I get this graphic. So I'm doing show of the background. And remember, the background is just the triangle and the three plots on the corner. It's list plot that's doing everything else here. I'm feeding it a list. And just because I wrapped each argument in that list with tooltip and button, I get this cool interactivity. So here, if we look up in this corner, you'll find all your linear type molecules. Where the molecule falls on this in this triangle, and they all will fall in the triangle, describes its shape. So you'll find your flatter molecules down here, right? Closer to the edge, and then you get your farther up to the left, you get the linear molecules, and then your rounder molecules as you go over here. And then I actually stuck a couple of ringers in here. This fluorinated fullerene, which is kind of a real distorted shape, and then we've got this C70 molecule, which has got a nice football shape to it. And then way over here in the corner, somewhere here, I've got fullerene, and then this guy. And so what is this guy, right? So that's where the button comes in. I'm hovering over it, I'm seeing the tooltip, and I click, and now that is in my clipboard. And so I can ask, what is its name? And so it's methanamine. I could also ask for its PubChem compound ID. And there it searches, and it finds this. And so it returns an external identifier. This is so it tells me the type of identifier it is, that it's a PubChem compound ID and the actual ID. And you'll see here that this is a hyperlink. I could click this, and in my web browser, it pulls up the web page for this particular chemical in PubChem. Right, and then this, yeah. So I think this is your the football-shaped molecule earlier. All right. So another application is MoleculeRecognize. So this is basically optical character recognition for structures. It's fairly neat. So you basically you take some. This thing is just an image, right? It's not a structure. It's something that I copied directly out of a PDF. Right, when I wanted to test this function, I just went and got a bunch of images from PDF files, and I say that's my image, and then it's literally image open close, and then I can do MoleculeRecognize on it, and so that takes a second the first time you run it. It's got some burn in, but it'll basically look at that and try and infer the actual chemical meaning of it. And there's more examples in here. So in this notebook, there's a grid of a bunch of molecules that you guys could play around with if you like. Right. So we are running a little short on time, but I've just got a few more applications that I want to highlight here. I talked a lot about PubChem, and I think it's a very useful service, and so their API allows similarity searching. And so, as we talked about earlier, you can create a molecule and you can ask for its PubChem ID. And then you can take that external identifier and you can create a new molecule out of it. You'll find that they're about the same. But what's interesting, though, is that you can then, using this resource function, and to anyone who's unfamiliar, so basically the way that this works is I type resource function PubChem similarity search, and then when I evaluate that, it highlights in my notebook using having this box. And basically you can use that box as the head of an expression. So I feed it the molecule we just created, and it makes a database call to PubChem and asks, what type of what molecules do you have that are similar to that? And it returns this list, and I can grab any of them and convert it to a molecule and look at it. And you can see essentially that this is one example of a similarity match that it was found. So this was the original molecule, and this was the match that we found. And so that's very useful. Let's see, this one is also fairly neat. So you can take a molecule, create it from its name, tetramethylammonium, and then ask it for its point group. And so what happened in between those steps is you created the molecule from the name, it converted it to a smiles, and from the smiles we made a graph. And then when you ask for its point group, we know that the system knows that it needs to generate 3D coordinates, and so it does so, and it minimizes them with a force field, and then it determines the symmetry of it. And in this case, it comes back as being tetrahedral. As we said before, you can ask for that in string form also. So let's see, let's make sure that we've evaluated the M as that, and now we can do the symmetry plot. And so what it does is it finds all the planes of symmetry, and allows you to highlight them or turn them off. We can find the S4 axes, right? So remember, so what this S4 axis means is that if we did a 90-degree rotation around that axis, and then we do a horizontal or do a reflection through the plane perpendicular to that axis, we end up with the same molecule. Yeah. And so again, that is a resource function. It's not a system function, but you can use it exactly the same as if it were. And I will just briefly show these last two slides that you can take a given molecule and you can ask for resonance structures of it. So in this case, you could take ozone and look at the two different resonance structures of it. You can take benzene and look at resonance structures. And again, using the function, you can molecule equivalent Q, you can test that these two are considered to be the same molecule, but sometimes you want to draw one Kukuli structure or another. And then you can take a more extreme example of this particular molecule with 4-bromo benzamide. And you can see that we've got two different phenyl groups here, and we have a naphthyl group. Or wait, not with those nitrogens. I'm not really sure what the name of that group is. But anyway, there's lots of room in here for the double bonds to move around and create different resonance structures. And likewise for tautomers. So in a resonance structure, you have electrons moving around. You've got double bonds changing position in tautomers. You can have mobile hydrogens as well. You can have not only have the electrons moving, but you can have the protons moving as well.